section 4.3.1, Gauss's law in dielectrics. Previously, we have considered having an object with some polarization P and finding the electric field from the polarization. But this is missing something. This is missing the fact that there is also an electric field that is generating the polarization. Okay, so we can't ignore that electric field anymore. In general, the polarization that we have been talking about, or the field coming from that polarized object, has to do with bound charges. So we are able to calculate the bound charges and calculate the potentials associated with those bound charges, and then we can use that to find the field. We have previously been talking about just charges in general, right, in the first couple chapters of the textbook. And what we need to now is introduce, not necessarily a new charge type, but a new definition of the charges we've been using. Okay, so bound charges refer specifically to charges that are associated with a dielectric, with some material that doesn't allow the charges to move freely, and they're paired up. Right, they're a result of polarization. There are also free charges. Now, those are all of the charges that you probably thought existed before. Charges that are independent of polarization. They are just existing on a surface or in a volume or whatever. And now we can go ahead and define the total charge as the sum of those. Okay, so this total charge density is related to the bound charges plus the free charges, rho f. Okay, so with this in mind, we can then calculate what the total field is, the field that the resultant field of an electric field that generates the polarization and the polarized object itself. Okay. So let's go ahead and start with a differential form of Gauss's law. Right, epsilon naught del dot E is equal to rho. Right, I just moved the epsilon naught over. Now we have two types of charges here. So let's go ahead and write that that's the bound plus the free. But we have a special way to write the bound charge. Bound charge is the negative divergence of the polarization. Right. So that's the electric field now is not, the electric field is the total electric field that we measure. It's the result of the two types of fields that I tried to describe earlier. Okay, so it is the total ending electric field. I can go ahead and bring that divergence term over to the left, and I'll be left with del dotted with sigma naught electric field plus the polarization, and that is equal to the free charge density, rho f. Now this term right here, we're going to give a special name. We'll symbol as D, and that is the electric displacement vector. Okay. And then I can go ahead and rewrite the above expression as del dot D is equal to the free charge density, rho f. That looks a lot like Gauss's law, and we did the trick earlier where we turned that differential form of Gauss's law into an integral form. I then have the surface interval of d dot dA must be equal to the total charge that is free and enclosed. Okay. This looks a lot like Gauss's law, right? So let's go ahead and apply that. So I can do example 4.4. I have an infinitely long wire of surface charge lambda. That wire is surrounded by some dielectric. With radius A. And I want to find the electric displacement. Okay. Done Gauss's law before. Let's go ahead and do this. Gauss's law here. Let's draw our Gaussian surface. Let's first do it inside. Distance S, length L. Keep the red. Okay, so the surface integral of d dot dA is going to be d times 2 pi SL, and the Q free enclosed, the free charges all come from this lambda here, and the amount that's enclosed is lambda times L. So d then becomes lambda over 2 pi S and the S hat direction. Now let's do this outside as well. I get d 2 pi SL is equal to lambda L still. D is equal to lambda over 2 pi S hat. Well, they're the same, right? I think maybe that's not so surprising that they're the same, because this expression only cares about the free enclosed charge. The free enclosed charge all lives on this wire, so it doesn't care about the polarized object itself. The electric displacement is the same throughout all of space. Now, the electric field isn't the same everywhere. The electric field inside and outside, because we have defined D as equal to epsilon naught E plus P, if the electric displacement is the same everywhere and the polarization changes in different regions of space, that must mean that the electric field also changes in different regions of space, namely inside and outside of this dielectric of size A.